Okay, in this lecture we are going to expand our understanding of work from a mechanical standpoint into a broader definition of what we can use in thermodynamics by looking at how to model expansion and compression work. So let us consider a closed system of a gas or liquid in a piston cylinder as the gas expands. During the process, the gas pressure exerts a normal force on the piston. The work done by the system as the piston is displaced a distance dx is, so our differential work is going to be our pressure times our area, which is our force, times our displacement dx. Now AdX is the change in volume of the system, dV. So our differential work is P dV. For expansion, dV is positive. For compression, dV is negative. So these agree with our previously defined sign convention for work. The change in volume from V1 is the change in volume is V1 and V2. So our work is equal to the integral of V1 to V2 of P dV. To evaluate this integral, we have to have some kind of relationship between the gas pressure at the moving boundary and the system volume. So during an actual expansion or compression, having a relationship is very, very difficult. And sometimes it's impossible due to non-equilibrium effects that are present in your system. Some of these effects, for example, could be combustion. In applications such as that, your work can only really be evaluated experimentally. However, some processes can be idealized where the pressure in the work integral is the pressure of the entire quantity of gas that's undergoing the process and not just the force on the piston face. We're going to call these idealized processes are called a quasi-equilibrium process. So all states through which a system passes in a quasi-equilibrium process are considered equilibrium states. So we're going to consider a process, and I'm going to draw on this figure. So I have a graph of pressure versus volume. I have state 1 and I have state 2. And I have an area under my curve. This is my path where my differential work is equal to P dV. The area is equal to the integral from 1 to 2 of P dV. Sorry, my differential work is just this little area. So the work done by the gas on the piston during expansion is given by our integral of P dV, which is equal to the area under the curve. If the gas was compressed from state 2 to state 1 along the same path, the magnitude of the work would be the same. However, our sign convention would change. So what I want to consider again is if I draw a very similar graph, I'm going to put state 1 here and state 2 here. The first curve I'm going to draw is curve A, which has area A under it. And then I have curve B, which has area B under it. So area A does not equal the area of curve B. So the work for A does not equal the work for B. And this just further demonstrates how work is process dependent, which means that work again is not a property. The pressure volume relation can also be described analytically. A quasi-equilibrium process described by PV to the N equals a constant is called a polytropic process. And for the special case of N equals 1, we have PV equals a constant. And if PV equals to a constant, our work is equal to the integral from 1 to 2 of P dV, which equals the integral from V1 to V2 of a constant over V dV, which equals a constant times the natural log of V2 over V1. So we need to evaluate the constant C, and that constant C can be evaluated at either state 1 or state 2 because C is equal to PV. So we get our work is equal to P1 V1 times the natural log of V2 over V1. And again, this is only valid when N is equal to 1. If N is not equal to 1, we're going to get a different expression, and we're going to actually determine what that expression is by working on a problem. We have carbon dioxide as a gas in a piston cylinder assembly. It undergoes 3 processes in series that begin and end at the same state, so it undergoes a cycle. Process 1 to 2 is expansion from state 1, where P1 is 10 bar and V1 is 1 meter cubed. State 2 to state 2, where V2 is 4 meters cubed. During the process, our pressure volume relationship is related by PV to the 1.5 equals a constant. Process 2 to 3 is a constant volume heating to state 3, where P3 is 10 bar. And then process 3 to 1 is a constant pressure compression back to state 1. We're going to sketch the process on a PV diagram, and then we're going to evaluate the work for each process and the net work for the cycle. Okay, so what do we know? Well, we know that we have CO2 undergoing a cycle. We're trying to find the PV diagram the work for each process and the net work. We can assume for 1 to 2, PV to 1.5 equals a constant. For 2 to 3, we have constant volume. And for 3 to 1, we have constant pressure. All right, so we're going to work on our solution. So let's draw our PV diagram. So we start at state 1, which is 10 bar and 1 meters cubed, and we have an isentropic expansion. So I'm going to put a curved line, not an isentropic, sorry, a polytropic expansion. Then we have constant volume, and then we have constant pressure. So that's what our cycle looks like on a PV diagram. Sorry, we actually don't know P2. So we're going to find P2. So we know that P1 V1 to the 1.5 is equal to a constant, which is equal to P2 V2 to the 1.5. We solve for P2, we get P2 is equal to P1 times V1 over V2 to the 1.5, which equals 10 bar times 1 over 4 to the 1.5, which equals 1.25 bar. So for process 1 to 2, our work is equal to the integral of PdV, which is equal to the integral from V1 to V2 of C dV over V to the n, which is equal to C times V2 to the 1 minus n minus V1 to the 1 minus n over 1 minus n. Where C is equal to P1 V1 to the n, which is equal to P2 V2 to the n. So this gives us that our work is equal to P2 V2 to the n times V2 to the 1 minus n minus P1 V1 to the n times V1 to the 1 minus n over 1 minus n, which is equal to P2 V2 minus P1 V1 over 1 minus n. And this is your equation for work for a polytropic process when n is not equal to 1. So for our process, our work from 1 to 2 is equal to 1.25 bar times 4 meters cubed minus 10 bar times 1 meters cubed divided by 1 minus 1.5 times 10 to the 5 Newton per meter squared per 1 bar, and 1 kilojoule is 10 to the 3 Newton meters. We get our work from 1 to 2 is equal to 1,000 kilojoules, and that is work out since it's positive. So then we have process 2 to 3, which is constant volume. So V3 is equal to V2, so delta V is equal to 0. Our work is equal to the integral of PdV, which is equal to the integral of 0, which is equal to 0. So the work from 2 to 3 is equal to 0. So the work for a constant volume process is 0. Last one we have is process 3 to 1, which is constant pressure. So work is equal to the integral of P dV. Since pressure is constant, it can come outside of the integral, which is equal P times V1 minus V3, which is equal to 10 bar times 1 minus 4 meters cubed times 10 to the 5 Newton per meter squared per bar times 1 kilojoule is 1 Newton meter. We get minus 3,000 kilojoules, which is work in because it is negative. Our net work, so W cycle is equal to work 1 to 2 plus the work 2 to 3 plus the work from 3 to 1. So it's 1,000 plus 0 minus 3,000, which equals minus 2,000 kilojoules. So the net work is into the system. I'm actually going to skip doing this problem. The solution is posted in the completed notes online. Please feel free to ask me for questions in class. I'll do it during class time. So a few other examples of work to finish up this section are the solid extension of a bar. If we have a bar and we pull it, we have sigma, which is our normal stress, and F is equal to sigma A. So our differential work is equal to minus sigma A dx, very similar to that problem we've done previously. We have power transmitted by a shaft. So if we consider a motor that has our current coming in and has a shaft rotating, our shaft work is going to be, our torque is going to be equal to our force, our tangential force times our radius. Now our velocity is r times omega, so our linear velocity is our radius times our angular velocity. So our power transmitted is going to be our work. So our power is our tangential force times our velocity, which is our torque over our radius, times our radius times our angular velocity, which is our torque times our angular velocity. For electrical power, we have our electric potential, epsilon, and we have I, which is our current. So the rate of energy transfer by work, for electric work, we have our potential times I. I is actually our differential electrical charge that flows. So our differential work is equal to minus epsilon dc. And our electric potential is really voltage. So this is really our P is equal to VI. In our next lecture, we're going to go over the different modes of heat transfer. So once we have work defined, once we have heat transfer defined, we can actually define the first law of thermodynamics.